Hi, this is Bill Foote, and this is NBA 611, uh, officially called Advanced Data Analysis, but I call it probabilistic reasoning for practical people. We use a Bayesian hypothetical deductive model to reach some interesting conclusions, and those conclusions are inferences, and inferences is learning, and it's all about counting in the end. This is the second video for week one, our first week in the course. And what I want to do is demonstrate using R as a tool to solve some of the problems that we reviewed fairly deeply uh, in the handwritten version of the model, which is in video one. And we will be using very much the same frameworks, but the difference here is we're going to be a little bit more expressive in terms of visualization. Pictures tell great stories. Let's see if we can tell some reasonable stories using the ggplot grammar of graphics package, Hadley Wickham's package in RStudio. Without much further ado, let's visit that studio right now. I don't think anybody's home, but there we go. This is what I want to walk through today, uh, and I've entitled this "Opening and Closing." Now, throughout the course, we're going to be using R Markdown, and if you're in RStudio, you go to File, New File, R Markdown. You could also use a Quarto document. I know very little about Quarto. I have invested all my time and energy, oh, and emotions in R Markdown. So let's pull this up. A template comes up. There are other templates, by the way, that are possible out there. But we're just going to use a document template, make it an HTML file, and call it, in this case, just as over here, uh, opening and closing. Well, yeah, we need to take the untitled part out. Now, when we check this box down here, what you will see on the left in line 4 in the YAML, which means yet another markdown language, like Yak from years ago, yet another C compiler, between three dashes. This gives direction to the rest of the document for rendering it as, in this case, output HTML. Could also use PDF and Word, have at it. But when we check that box, it uses the current system date by calling up a piece of code, a piece of R code, sys.date will give you the current date. Say OK. Oh, there it is. And a template comes up, just as we predicted. We're going to be using some packages, uh, library rethinking. That's one. We're also going to be using the tidyverse. That's another. And, well, we're going to use something made just for us, tidybays. We may use other packages as well. And notice that in the R Markdown, um, we have headers for each section. We also have some words we can write here. So this is in the manner of a notebook like Jupyter, um, if you're familiar with that, and code chunks as in Jupyter. Very, very similar, but you know, this works for me. I like the panes. I like the environment and the history. Very little. Oh, there's some history here. Oh, definitely lots of history. Um, Files. I mean, I can plots. Well, no plots today. They're actually inline. And the console down here. a REPL console? REPL, look that term up. Well, okay. If we have all of this going on, well, let's build something here. From over here, I've already got all this done, and this is on the Moodle site. I have a thing called Consider This Approach. I'm just going to copy and paste it over there. I just want to show you how easy it is to do some of this. And also the first routine with a plot. We're going to get right into it and walk ourselves through the mechanics of this. Just copy and paste into this untitled amalgam here. Okay. Now, what we have done here is we have some directions. Include equals false means none of this is included. I'm also going to include something called options digits equal to and scientific penalty equal 99999. Okay, for scientific expressions like 10 to the minus 138th power. Okay, we're going to get rid of that sort of idea. But here I'm writing, consider this approach. Okay, there's an end in sight. That's the final cause. We have a framework. That's the formal cause. This is Aristotle 101. You answer questions associated with end in sight, framework, materials to work with, and inference, which is us. We're the agents of change here. You have a complete report. Okay, so we're going to form hypotheses and a procedure to count the way actual closings and openings that we may have sampled could be consistent with those ideas or conjectures, otherwise known as hypotheses. So we've been through all of this. That's the formal cause. The materials are, well, code. There's a lot of code here, previous experiences, actual occurrences, the material cause, and inference is the decision maker deciding on, before the decision is made, making other decisions on what inference means to the decision maker, the consumer of this analysis. So here's a basic opening and closing. There's going to be two ways that we're going to do this. There's one way, and there will be another. But let's just walk through this. We're using the tidyverse. Okay. There we go. It's in there. And from the tidyverse, we're going to build a simple data structure called a tibble. This is a data frame with a bunch of other exclusions associated with it. And we're going to call it D1. That's what the assignment operator is, a binary operator, what it does. And inside of the tibble, there's going to be two columns, an open column with a single digit in it called 3, and a closed column with 6. So 3 are open, 6 are closed in this basic thing. I mean, if you type out D1, there we go, real simple. There's the columns, only 2 items in it. And this is just very formal, but I want to be this formal because I want to use this structure, with much more complicated data structures after this. We're gonna say size is 3 plus 6. Well, how do we get that? We take D1 access. See, it automatically knows what you're looking for. How clever. The open number plus D1 accessing the closed number 6. So if we go up here and press Control Enter, that's put into dynamic memory. Well, no, it's attached somewhere that can be accessed. And size. Okay. Now here's our grid. We're making a grid, which will be a sequence from 0 to size minus 1. Well, what is size? Down here and look at that. Size is 9. Size 9 shoes. From 0 to 8. Well, it's because we want 9 possibilities, but we're gonna size this to 8. 0 to 8. So our grid's going to look an awful lot like our data in a sense. And we can say from 0 to 17. Okay, would be fine too. Or give me another prime number out there. Any other 41 maybe? Yeah, okay. 7,300 and something is the largest prime we need to generate any other primes. And with a length of size out equals length out equals size. These are going to be our hypotheses. So using the sequence, let's just do this like this. This is how I remember stuff. Sequence from equals 0 to equals 1. No, 2 equals size minus 1. And that's just a choice. I could choose other things. Length out seems to be required these days. And length out is size. Now, these two are going to be very consistent, and you'll see what happens when we make that grid. Zero to 8. Okay. And we're going to have an improper, because it's a 1. But remember, everything was multiplied together. So we're just taking our paper and pencil method and throwing it into, basically just throwing it into not Excel or Google Sheets, but this time into R. And this is a repeating 1. Repeat, replicate a 1. How many times? Size times. Okay. But this will work, and maybe you need to go back and see why it will work. There's a bunch of 1s. The length of prior, and these are our prior beliefs, we think everything's the same, is 9, the same length as P grid. Now, posterior, the probability, this is going to be the probability. We use comments. That is a hash mark. This is the probability of H given D that we discussed. Not a curly brace there. There you are. H given D. If D, then H, how probable is that truth? Okay. Not so probable, closer to false. Yeah, okay. Probability becomes a plausibility score. Are we close to false, which is 0, or true, which is 1? Are we somewhere in between? Is it an ordered somewhere? Are we, because now we can measure distance. We can say how close we are to 1, certainty about it being true, or 0, certainty about it being false. Okay, 2 levels of certainty and a bunch of uncertainties in between. Okay, there's a lot of texture in that. We're going to call this a posterior. But in order to get that, we have to compute all of the ways. And this was part of something else we did. We did both and if we just take this P grid open, I can just write it down here. Take the entire P grid and raise it to the number of openings. That's D 1. That's 3 of them, right? We get that sequence of ways in which the openings, all 3 of them, can impact the grid of all of our, the 0 to 8 grid of all of our hypotheses. And then we can reverse the order. We could use arithmetic to do this, but I just wanted to introduce a new function, the rev function, the reverse function. It's like a ravel function. It ravels it around until the order is reversed. Okay, that's an interesting idea in and of itself. And notice that this is, oh my gosh, a lot more. Now notice we go from 0 to a big number, but we go from a huge number to 0. Okay, so both of these are multiplied together with the prior. Now the prior could have been, 1/9, by the way. And if we take all of these together, we look at the ways. Trying to get to, there it is. Those are all of the ways. Notice they're integer ways, which is kind of nice because it's 1/9. We're using integers and rational numbers, which are ratios of integers throughout. So these could be all of the ways. It doesn't matter as long as our prior beliefs, which in this case are uh, a number between 0 and 1, including 1, the multiplication will always work. But look how it conditions the ways. If we had set the prior to 1, this is why I'm doing this, so we can play with it a little bit. Quite a bit different, huh? 117,000 ways gets whittled down to 13,000 because of a belief that 1/9 of the time the first hypothesis, 1/9 of the time the second, and all the way down to the ninth hypothesis. We have 9 hypotheses here. So we can do a lot more than the paper and pencil because after a while I've got my writer's bump here with my number 2 Ticonderoga pencil. And well, I just don't need it hurts sometimes. Anyways, too much information, huh? And then we take all of those ways and divide them by the sum of the ways. Now, this is a normalization approach. We have each of these ways. If we calculate the sum of the ways, notice it cleverly includes the right parentheses. We have 1,280,208 total ways in which this data can interact with those 9 hypotheses. And that's interesting. That's interesting. If we now take all of those ways, those, 13,000 or 117,000 ways divided by this number, we get an idea. And look, it's even bigger and bigger and then goes down again. So one, two, that third hypothesis, no, the fourth hypothesis seems to dominate. We can get a score between 0 and 1. Okay, no problem. Standard weighted average approach to life here. So let's just do that. And there they are. There's one close to 1/9, nearly 30%, almost 33%. 20. These do not need to be exact. What needs to be told here is how are they looking relative to one another? And everything is tied down at either end with a 0, just as we had in our other discussion. Okay, we can use something from Rethinking, McElry's Rethinking, do the Précis, but it doesn't like it. Don't ask me why. Very strange. Oh! I know what that is. This is the histogram. It didn't like it at all. Oh my gosh, fascinating. Okay, it produces a histogram, so we don't even need this because we don't like errors we really don't understand. There we go. All right, and now let's plot this, and I'm going to use the grammar of graphics, and you'll get used to doing this if you do it about 100 times. And then all of a sudden, I can make plots very easily in this framework. Now, this is a layering approach, uh, just like Adobe Illustrator uses the same idea where we layer images one on top of the other. Pixels on your television set do the same thing. It's a layering of multiple signals, and eventually you see red, green, and blue, and black and white, and all sorts of other cool things, all hashed together into high definition. But here's a tibble again, and we're creating a data tibble. I'm going to call this D for the moment. A data tibble that we're going to feed with something called, this is called a pipe. And how do you write the pipe? Shift backslash. It's a key above the enter key. Keep the shift on. A greater than sign. That's a pipe. So D, this D object is now fed to ggplot. That's the data. It's fed to it. AES is the aesthetic. The aesthetic basically creates a grid. Let's just do this like this so you can see it. And if we just did P1 and we assign this to a function or an object called P1, there we go. It's just a grid. It's a blank canvas. That's all that does. But it starts now. Now we start layering things onto it. We can layer text, lines, all sorts of geometries onto it, geometric objects, because it's nice geometric space. Perpendicular lines. I was hoping that they'd be able to do affine spaces. You have parallel lines, but you don't need perpendicular. That'd be really cool, but we're not there at the coolness yet. And then we put points in it. Okay. Let me show you that. Shift enter. Do P1 again. And voila, we have superimposed points. And nice, very nice drawing. Okay. We can superimpose some other things on it, like a title, a subtitle, appropriate. I think we want to put P here. We can't. Oh, there it is. And the probability of 6 closings in 9 observances. I don't know if that's true. But I want to add one more thing that is required on all your work. It's called a caption. Now, there's 2 ways of putting a caption in our Markdown. One is to throw a figure caption way up here in the definition of this chunk called a code chunk. Right now it's with R, and we can put a caption in there. But we can also put it down here. Oops. Oh, what do we want to call it? This is documentation. Okay. And you'll just, this is not an English sentence yet. There. Now it's a sentence. And it's important to have good grammar in the grammar of graphics, huh? Okay. So let's throw all of these things together and see what we get. I guess it wants to put it down here. Notice it does that. Now I can thematically put this in the middle, left justify it. I could use a font, all sorts of cool things to make it look, and also position it in other ways. But here's your basic graph. Okay, these are just points. I could put bars underneath it, which we'll do next. And kind of cool. All right. So far so good. Everybody okay? Okay. Let's what's the high point here? Well, we should probably put in a V line here, a line going from here to here at this high point. Now let's see if I can remember how to do that. If I were to do this, max underscore P, what is, okay, the maximum posterior probability. Oops. Alt dash will get me that assignment symbol. And if I look for the P grid value, that's the bracket where I can search through, there's various indices. P grid has what, nine elements in it. Which dot max, something else has 9 elements in it too. Which dot max in the posterior, in other words, the index. This is index and match from spreadsheet days. And if I do that and just look for max P, it says it's 3. I guess it's number 3. Okay. And let me look at something here. Yeah, it's going to be number 3. The probability of closing it on itself using P-grid. Okay, 0 to 8. Right, so that's correct. 3. But I mean, that isn't a probability though, is it? So we might want to try something a little different here, in which we say P-grid for the data purpose is P-grid divided by 9. Let's see how that works. And why by 9? Well, that gives us the probability, the proportion. It was 25, 50, and 75% before in the handwritten version from the first video. And let's look at what max P looks like here. Oh, it's still 3. Okay, something did not. Oh, I see. Okay. I'd have to divide this by 9 and get the arithmetic right. It's all about arithmetic, isn't it? There we go, 33. Oh, I think that makes some kind of sense. If I took pgrid, divide it by 9, let's look at what that looks like. Ah, there we go. There we go. 33, 44, 56, all the way up to 89. How come this doesn't go to 100%? Do I need to make it go by 8? I do. Because we lose the 0. There we go. Now we're correct. Arithmetic, huh? It's 1 to 8, but got to remember there's 0 in there. But okay, fine. Okay, cool. Now, if I put another line in here, geom v line, and say, well, what do you think? We're making a vertical line. We probably need to use the x-intercept. Better kind of like put it in here. There we go. The x-intercept, see, it knows it, equals max p. Make sure you add that layer in. Oh, let's give it a color. Red, of course. And a size, a thickness. About 1.5 times its normal thickness. Let's see what happens. Oh, cool. Yeah, it blew through that dot up there, right? And I'm going to put an H line so that we have an easier to read axis. Okay, let's try that idea. See, now we have proportions which look like probabilities, so now that looks more correct. Okay, so we fix things on the fly in order to tell the story. Let's put I'm going to take that. That's just too thick for me. There we go. And a geom H line. Now here we need a y-intercept. Equals 0. And what that will do is put a horizontal line, the x-axis, for us. Okay. There we go. Finally, I want to make this a line, a frequency polygon. Now there's a geometric object called polygon in there, but I don't want to use that because I just like doing it the old-fashioned way. Okay, geom, come on. There we go. Geom line. Just see what happens. I think it's just going to come out like a black line. And that'll make the frequency polygon. And finally, I want to put a point after that vertical line where we're indicating where the maximum probability, maximum parameter. P is actually a parameter. Remember, I was talking about the parameter space being whatever it is. It's random. It's indeterminate. That's the whole feature of this Bayesian approach. In the other approach, the frequentist, we actually calculate a number and then kind of bootstrap how things change around that number. We get that directly here. Well, we'll see how directly it is. Geom underscore point. And now I have to use another AES to define an X. Now the X will be the max P along that axis. And a Y will equal this max probability. I just want to put it down here, which dot max, not wick. No, I want to do something different. Max of the posterior. I mean, this is a great big scatter plot. Okay, that's 33. That is 33. Max P is 38. Good. Yeah, the data is not the same as, and the proportion is not the same as, I mean, what's 3 and 9? That's 33 and a third, right? Yeah. So the data proportion and the hypothesis proportion are different. Keep that in mind. That parameter is different. We'll have a discussion around that at some point. We're going to call this, just do max posterior for the moment. We should define that variable outside. That's the right way to do things. Check. Okay, that's good. That's good. What am I doing? I'm checking the parentheses. Ooh, there we go. Catalan numbers. And let's make this red as well. Okay. Size equals 1.25. Make it bigger than the line. Okay. Let's see if any of this works, because I'm doing it on the fly. It did. Oh, I don't like that. That should be over here. Okay, so I got some work to do yet. That line should definitely be over here. And what work might that be? I have a cheat sheet over here. That might help me. You've improved this tremendously, by the way. Congratulations. We can also make this sort of thing using a geom bar and treating the p-grid divided by 8 as a set of categories. That's how you make bar charts, with categories. But the thing I'm looking for is down here. No, I did it right. Max p equals p-grid equals that. Okay, we're gonna walk through this in a moment and be done with it and wash our hands of all this. And do inference on another session. And I think I'll do that in inference in another session, because this is already going too long. But so we've gone from here, and we need to see that in this one, that's over too far. We need it to be over here. Now, what is over here? There's another package that we could use if we were to install .packages, and you have to use quotes with this, Plotly. Oh, I think I already have this in here. I might have this already in here. I do. I'll use that. Okay, cool. So let's also put Plotly in here. And watch what I can do with that. It makes my graphs interactive in HTML. How cool is that? Well, very cool to me. Okay, so now, because I did that, I can go down here and do ggplotly of that object. Watch what happens. Still running. Okay. There it is. It's the Plotly version. Now watch what happens. I can see what that is. Notice, I think what's happening here is 38. No. That's 38. But this coming up here should be a P grid of 33. And why that is, we need to investigate. Now, I'm shooting trouble. Okay. I don't have an answer. Maybe you can figure out an answer. Oh, by the way, that's what Plotly can do, is do that. Look very closely and zoom in. It's called a brush, and it works beautifully. Very good. Down here, let's brush this. There we go. We can get that. Oh, there's that thing. We want to make that bigger, that red dot. And we need to figure out why these two are different. And I'm sure it's my bad programming of which dot max. As I am notoriously, everybody who's ever worked with me knows this about me, notoriously dyslexic. Should I put this here or should I put this here? What is that? This looks right, but okay. Anyways, enough of that. This is the reason. That's the reason. Aha! I think I got it. Bang. See? I made an error somewhere. Now we can also annotate this and do all sorts of other cool things. Note that we need, and notice the caption's gone. Plotly does not like captions, which means we have to put the captions. I forgot about that. We can put Plotly captions in, but it looks a little more complicated. And how much time do we really have? Not much. But I can also put into this all sorts of other vertical lines. And I just want to illustrate what's going on down here. Having done all of that, I showed you the bar that you can put in by making the probabilities factors. But the other way is creating a grid from 0 to 1. And there's the grid. Oh, how many of them? 101 Dalmatians. Yeah. 0 to 1. Okay, so and everything in between. Notice I had to make that. And I'm calling these vertices. And they're joined by lines called edges. So I'm thinking as in graph theory, very important stuff. And these are our hypotheses. Prior is still going to be this goofy prior. Okay. Size of 9. Well, we have 9 observations. 6 of them are closings. And now we create something called the likelihood function, which is let's just go ahead and do it and show it. There we go. It's a bunch of probabilities. Now, this does not add up to one. These are just picked probabilities that are picked out of a bunch of other ones that could possibly occur. But this is the binomial model density. This is X or K. This is N. And we're using all the probabilities as the p-grid values from 0 to 1, that 101 of those. So this is a vector operation. It's beautiful. Takes it all in at once. And what did we do before? We take the likelihood, create, multiply it all by priors. But there's something I didn't do here that I need to do. I need to take the product of all of those likelihoods. Yikes. And it doesn't like it. Oh, prod probably. I can't remember from one day to the next. There we go. Now look at the posterior. Well, it's not quite the posterior. We take this and divide it. So I don't want to make this. This is just call it X for the moment because it doesn't have a really good name. And take all of those products and divide it by the sum of those products. So we did this, and now we have a posterior. I'm sitting on one right now. And it's all not a number. Okay, so I got some work to do here. But I think what we can do, we have all of these closings on the P grid. No, I did this wrong. I had it right the first time. And how do I know I had it right the first time? Well, that's because I need dinner, I think. But so you look at the posterior now. You don't need a product there. Don't do this on low blood sugar. Very dangerous. Needs an O pill. There we go. Okay. Now if we take this the likelihood already has all this is already done all of those. That's what the binomial model does. It does all of those products that we did before. P grid raised to the number of opens, P grid raised to the number of closing, multiply them together, multiply all of that times the prior, and now you get your quote unquote likelihood or prior, or whatever we want to call it, X. And then we take all of these down here, sum them up, and use that to normalize each one of these so they're going to be able to be compared nicely. So we're going to do that. Same procedure as before. And there we go. So these numbers are a little bit easier to digest. It should be 0.02. And finally, try to do all of these these hijinks. Make a new grid. Okay, we got the old grid and posterior. Do that, make a label. And inside of this, use a caption. I use annotate text. Here's the coordinate where the text is going to be centered, and use label as, well, paste 0 is concatenate this text with this piece of data that we just produced. When we do that, we have this lovely piece. And one last thing is inference. And I'm just going to show this to you. We'll probably go over this a couple of times. But with the same problem, okay, we now say 89% of the time we want our p-value in the p-grid to be between a lower and an upper amount. But we have to calculate those lowers and uppers amounts. Those are quantiles. So we produce a lower probability of 5.5% and an upper probability of 5.5% plus 89% for 94.5% upper. We then reverse the process and ask the question, out of all the samples, oh, I forgot to say we made samples. Oh my God. Here, samples. We made samples of p-grid values, of parameter values, but using the posterior curve. Interesting thing, and do 10,000 of them and with replacement. We'll go over this again and again and again. We did that up there. Now we're taking those samples and looking at the quantile for the lower and the upper. Just look at what the lower is. The lower is 0.4. So between 0.4 and 0.85, remember those are probability values, 89% of our plausibility is in between those. Now, if we have more uncertainty, they're going to widen. If they have less uncertainty, they're going to tighten. Okay, that's the bell curve for you. And then we're going to make a lower label and an upper label with that paste 0 feature. And we're going to plot this thing. Look at this plot. A thing of beauty. I like the yellow. Lower bound, I got to fix this a little bit. And the upper bound. That's what the manager wants to know. We might put 89% in here or some other thing. Using annotate text, the geometric object that is being introduced there in the annotate is called text. Okay, it's a text box with a x lower minus 2. There we go. This might fix it. So is your head spinning yet? Hopefully it is. There we go. A little bit easier. I would try to probably put it over this over to the right. But we have an almost, it's called a posterior predictive probability interval. Oh, you'll read that in McElrath for sure. And come out singing. Posterior binomial samplings of 6 closings and 9 observations. It's dynamic. We change it. If we change the number of closings and the number altogether and the number of observations, all of that gets dumped into this label, which I probably should put up here. But a lot of interesting things that you can do here. Legend position. It will show a legend for some weird reason that I do not, nobody has been able to explain it to me. I also use percent scales on the y-axis, We also play with the caption to make it 12 font in the middle. That's what 0.5 means. The Garamond font face, blue, and the font face is bolded. Okay, the Garamond is bolded. Uh, yeah, there you go. Recipes for success to tell stories. This inference piece, we're going to have to go over a few more times because we're sampling and we need to do that with our parameters. We have only one parameter here and we just beat the daylights out of it. Okay, you can follow along in the piece that is loaded into Moodle and improve it with what we have done. With that, hoping all this worked out. With that, let's see if I can find where the Zoom piece is. And I think this is where it is. Yes. We're going to stop the share. I'm going to thank you all very much for your kind attention. Spent quite a bit of time on a relatively elementary thing, but we got a. I think you can get a lot out of it because visualization is going to be extremely important, and it's a great tool. It's a great tool to think this way in layers and making sure it's a complete story with a caption, subtitle, title. All of this is important to the rhetoric of telling a visual story, visual journalism, visual querying, visual reporting in general is now the norm because we have the tools to do all of this interesting computing. ggplot2 is also quote unquote aware. So it does some interesting things that I did not expect, like putting legends in that don't need to be there. That's why I had to take it out. It's a little bit too aware. So I'm going to leave you with that. Thank you very much for your kind attention. Remember to, in your teams, do this together and encourage each other daily while it is still today. I'll leave you with that. And thank you very much for your support in this course. It's great to be able to work with you. One more video, no, probably two, is a contingency table video coming up. And I think I'm going to do a little bit more on this HP, HPDI, the high probability, high probability density interval. Okay, it's credibility intervals. It's no longer confidence intervals. So I think we want to touch on that a little bit more. And then on Saturday, we will have a live session and go over the skill builder, which is the assignment for the week. Okay. Take care and enjoy the rest of your week. Thank you.